Thank you very much for coming to today's talk. This is part of our Math Science Division career talk. And today's speaker is David Ink, and he works at the Advanced Molecular Biology Lab at UBC. It's part of the old biotech labs, and now it's part of the Michael Smith Genome Center. And today we're going to talk to you about the scientific method and the need for scientists to advocate certain things. So he's going to talk about 35 minutes, and then he'll give you an opportunity to ask some questions. Okay? Enjoy it.
All right,
Take
thanks.
it away. Thank you.
Thanks very much. So thanks for having me out. And I noticed I was listed on the poster as a poster boy for biology. And although that is my background, that's my training. So I'm trained as a molecular geneticist. I have a PhD, primarily doing biochemistry work and cancer signal transduction. These days, my career is really about science literacy and science education and science communications, which for those of you who are currently going through your academic route as a scientist or some type of field where science is involved, it's actually becoming more common for these grad students or undergrads to think about a career in education or journalism or communications or PR or something like that. Partly because to be frank, the market, the job market for things like in academia is pretty tight, but partly because science literacy is actually, it's a huge deal these days. It's having huge effects in society, at the local level and at the global level. So I thought I'd come and just kind of tell you a little bit about what I do. I often show this slide because it kind of encapsulates the nightmares I have when I go to bed, right? So let me give you a little bit of context here. So this, you remember in Vancouver there was a heat wave about 2-3 summers ago, right? It was like freaking hot, like it was really hot. Yes. Oh, yes. So we don't need to tell you. Yeah. So I have 2 young kids, so they're like, "Oh, Dad, it's so hot," right? And it's like, "Oh, let's go get an inflatable pool." And I'm like, right there, right? Okay, let's go get an inflatable pool. So we go to Toys R Us, right? And Toys R Us, being the marketing gurus that they are, they have very nicely put all the inflatable pools front and center. The minute you walk into the store, you are like awashed with a bevy of different options for different types of inflatable pools, right? So we saw this one, right? And $19.99, right? Less than $20. And so it's like, yeah, we're so going to buy this, right? So we bought it, right? We took it home. I blew it up. We put it in our backyard. And so here's a picture of my kids, Hannah and Ben, standing next to the inflatable pool, right? And so I'm a science geek, so I'm always kind of thinking sciencey stuff, and I'm hypothesizing like crazy, right? And I'm kind of going, oh, what the hell's going on here? It's like, are my kids massive? Like that was one possibility. Or, was this photographed in a land of like hobbits or something like that? I don't know. Or did I not blow hard enough and I hadn't actually inflated? And well, it turns out that in the world of advertising, you can get away with stuff like this because it is actually legal as long as you have a byline on the box that says object may not be as appears, right? And I use this as an example of just sort of the state of science literacy and science media these days, right? Because often, you and I, we're trained in it. We're into it. I'm preaching to the choir right now, presumably, right? We know how science works. But often for the general public, what they actually see is a different form of it because of media or what have you. So this might be the reality, but this kind of is, it's been spun in a way, right? So this is what my lab is very interested in. And ultimately, we're interested in sort of hosting programs or developing initiatives that can kind of whittle away at this challenge of science literacy. Okay? Now, I said in my promo, I would talk a little bit about the scientific method, right? And I know before you kind of close your eyes and sort of tune out because you're thinking, geez, the scientific method, really? Really? He's going to talk about the scientific method? But I often feel, and so who here is an undergrad? Undergrads? Who here is a grad? Do you guys have grad students here? Grad? Okay, faculty? Faculty? Yeah, a couple of faculty. Okay. Staff? A couple of staff? Yeah, okay. Even though, I mean, you're scientists, whether you're at the undergrad or faculty level or what have you, right? But I find that the vast majority of scientists, they don't really think about the method maybe the way I think about the method, right? Because the scientific method is freaking awesome. I mean, it is very elegant, it's pretty, it's nuanced, it's not perfect, right? And it's not even this, because this is what you get in elementary school, right? This whole idea that you see something, so there's an observation involved. The whole idea that you think of a reason why, so this is the whole idea of, you know, coming up with hypotheses, right? Which is a key aspect of the scientific method. Figuring out a way to check your reason, so this is where, you know, you actually go through experimental design. What's the best way to actually figure out an answer to your question? Then there's this huge and, right? Which in grad studies means data, right? And this is the part that takes for freaking ever. And then everyone gets to dump on you, right? And maybe more importantly, you're relying on people who know what they're talking about dumping on you. So this is the aspect of expert peer review, also critical, right? And then you kind of keep doing this, or you repeat until a consensus is formed, right? So this is a very linear view of the scientific method, right? And I mean, the reality is that the scientific method is not linear at all, right? You might see something and you've done your science. You've discovered a new bird, right? In some respect, I still would consider you a scientist if you've discovered something new, right? Likewise, your data may tangent off into a whole new other inquiry or what have you, a new set of hypotheses. So it's not linear at all. And I think this is what's kind of missing in societies these days. Everybody gets the scientific method, right? When they're in elementary school, do you remember? I bet you did something with butterflies, is my guess, right? Or maybe something about dropping oil in Petri plates with milk in it or something like that, right? But at some level, for some reason, you don't really talk about it again in full nuanced glory unless you are maybe a science philosophy major at the university level. And I think that's wrong, because it is a really, really powerful way of thinking. It's a really powerful, fancy word is epistemology, way of knowing, right? And the public is a little out of touch. I mean, we all know about hypotheses here, right? This is actually, so I wrote this thing once about, there was this correlative trend in China in the early 80s. Okay, so let me set the scene here. So in the early 80s, in certain parts of China, they noticed that the sort of indigenous stork population was going down. Okay, so storks were disappearing. At the same time, they also noticed that fertility rates, right, in this same region was also going down. So less babies were being born, right? So here you have two observations. You see something interesting, and you're, you know, as a scientist, you're trying to figure out what kind of happened, right? So here are two examples. Maybe it's something to do with environmental pollution. You might imagine that could result in something like hormone disruption. That could result in fewer babies, likewise fewer storks being born, and you have a correlative change, right? Or maybe your hypothesis indicates something to do with an economic development, right? China is all about economic development these days. Because of economic development, you might have female job equity, right? So they're just going to work more often and not having children so much. Maybe it's all about urban spread. As the economies rise, you're more likely to be able to turn land into more residential, industrial, or what have you. There's an urban spread. Likewise, this will result in lower fertility, fewer storks, and there's a correlated change, right? So these two are just hypotheses. Now here's one that I posit, right? So space alien infiltration, right? And the reason why this works is because humans are considered pets, right? And therefore you are missing babies, right? And likewise, maybe these aliens consider storks as a galactic delicacy, right? They like to eat it, so you get fewer storks, and you have a correlated change, right? And what I'm here to tell you, right, is in all three cases, I would consider the hypothesis worthy. Okay? Because logically, they work, right? They do work. Now, whether it's valid, right, that's a different set of criteria. Because valid, you really need to show some evidence for what you're trying to present there, right? But it's very nuanced, right? I think we get it, but you'd be quite surprised when you go out and you talk to the general public, right? They don't understand that nuance, right? Like, how do you actually prove these things? Can you prove these things, right? For instance, I found a space alien. Holy shit, I found a space alien, right? That's evidence, right? That's evidence. Number 3 has got to be right. Well, no, right? Just because you find an alien, that does not address the hypotheses at all, right? It certainly doesn't hurt, and you could argue that if there's one major weakness behind this hypothesis, it's the evidence of aliens. True, but as far as directly sort of dealing with this hypothesis, it doesn't at all, right? So maybe you say, well, I found an alien, and get this, okay? It had a baby, and the baby was wearing a collar, right? And it was chowing down big time on a stork, okay? Right? This is better, right? But still, I mean, if you're scientifically trained, you're still skeptical because you know that in and of itself is still not that strong an evidence, right? Was the baby Chinese, right? Where did the stork come from, right? Was it a stork from China, right? And so you might say, well, okay, now I have a different kind of proof. I know the stork is actually from China because we've done the biochemical analysis and, you know, we've checked for different isotope ratios to make sure that it is indeed coming from this particular place or what have you. And likewise, we actually have video surveillance of the alien taking the baby, putting a collar around it, and actually talking to its alien friends as if it was a pet, right? All better, okay? Although here you want to run into a situation where you're starting to use more technical language, the experiments involved, maybe to the layman is a little bit harder to decipher, right? But it's still better evidence, right? You can see there's gradations in how you can address things like hypotheses, right? But even there, I would say that's not great data, right? Because you saw one stork and one baby. So how does that factor in the grand totality? Right? Just because you see it in one, it's no different than anecdotal evidence, quite frankly. Right? So these are nuances that the public as a whole tends to forget, and that's dangerous in society. Right? So this is an example of hypotheses. Ah, yes, my picture. I want to draw your attention to this panda here. This panda is relatively famous. I say relatively because I'm guessing no one here knows who the hell the panda is. But if you Google this panda, you'll actually see photos of the panda with President Carter, you know, Steven Pinker, Martha Stewart. So he's been around, this panda. And this was actually, I think, in 2006, because I'm that wild, I actually crashed a science philosophy conference. I know, that's wild. That's the definition of wild, is crashing a science philosophy conference. But on the upside, I met some friends, but on the upside, I got to meet Prof. Steve, so that's his name. Okay? So Prof. Steve is actually a mascot for a project that was instigated by the National Center for Science Education, which is a nonprofit based in the US. And the story goes as follows. Okay? So in 2003, the Discovery Institute, right, which is a nonprofit think tank in Seattle, conservative based, primarily a front for intelligent design and the introduction of intelligent design into the public school system, especially in certain states, actually issued this statement and asked for academics to sign it. Okay? And the statement, we are skeptical of claims for the ability of random mutation and natural selection to account for the complexity of life. Careful examination of the evidence for Darwinian theory should be encouraged. It's a very sneaky way of asking people to discredit the science of evolution. It's sneaky because, they've worded it very carefully that, you can kind of and on, but ultimately, because of the organization issuing it, it is sort of an attack on evolutionary biology, right? As of 2011, they have about 700 signatures, okay? But in 2004, the National Center for Science Education decided to release a competing statement. And this is the statement, right? I'll let you read it out. But basically, it's saying that evolution is pretty good. The science behind evolution is pretty robust, right? And, it certainly doesn't deserve to have that kind of attack on it, right? And when I last checked, as of December 31st, I think they're up to almost 1,200 signatures, okay? So 1,200 is more than 700, so that's good. Yay. But the two lists have a number of differences, okay? So firstly, the method of attribution, right? If you go through this list, attribution, like actually stating what the author, what their field is, where they're currently stationed, if they're retired, even if they have publications, that kind of thing, it's all over the place, right? Sometimes it's quite good, but a lot of times it's very vague, right? On the other hand, the NCSE list attribution, there's a particular format, follows it throughout for all 1,200 signatures, okay? Secondly, the actual backgrounds of the academics in this case are really wild and diverse, right? There are biologists, but there's a lot of other academics in other fields such as plastic surgeon, that's a doctor, right? Things like that. And, if you actually look at stats here, if you kind of look at the number of signatories and try to link them to a life science angle, depending on who does the analysis, it can be high as 50%. Right? Here, the numbers, depending on the analysis, tends to be maybe the highest is about 22, 23% or thereabouts. Okay? So definitely, if you think about it, the people who are signing this are kind of better adept at knowing about these things. Okay? So that's the second difference. The third difference is that everybody who signed this one is named Steve. Like seriously, everybody who signed all 1,200 of the signatories in the NCSE list, their name is Steve or Stephen or Stephanie or Stavros if you're Greek, or some sort of root from the name Steve. So their point is that we can beat you, right? And only Steves are allowed to sign it, right? And they've even done some sort of kind of weak analysis would say that within all of scientific community, Steves represent just under 1% of the totality. So from that, they would argue that if they did open this up for everyone, we would actually get like way more, obviously. Is anybody here named Steve?
We have a biology faculty who signed it.
Yes, yes. And here's the fourth difference. You get a free T-shirt when you sign this one. You actually get a special T-shirt. He's got the T-shirt? Yeah. All right. Now, I use this just to sort of bring up the idea of expert peer review, right? In many respects, this is an exercise in saying that if you're going to go with somebody's opinion, you would like to go with an opinion of somebody that knows what they're talking about, right? And so this is another key facet of the scientific method that, quite frankly, the public sometimes forgets. They do forget. In fact, the expert community is sometimes distrusted, right? It's a little scary, okay? This is all to say the following, okay? Because how science works and how the public gets its science is in contrast with each other, right? So for instance, I have this slide of Bruce Lee because my dad beat up Bruce Lee. Okay. Did you know that? My dad beat up. Do you guys know who Bruce Lee is? Am I dating myself? People know who Bruce Lee is, right? Yeah. So my dad beat up Bruce Lee. Like, no shit. I'm serious. This is true. This is true. My dad beat up Bruce Lee. My dad was 10, and Bruce was 8. Okay? Now, the point here is that I'm showing you how off-kiltered a soundbite can be, right? my first line, without that secondary line for context, they mean two totally different things, right? And this is how media operates. It's not because media is bad, it's because it has different pressures, right? From editors, from the people who buy the magazines or newspapers. They don't have the luxury to spend a long time on a story, right? That's how science works. It's a freakishly long story, standing on the shoulders of giants. That's what it's all about. When you do research, your research is sitting on the foundation of many, many efforts from many, many people before you, right? That's hard to do in a press clip, right? Media also has something called narrative bias, right? They like endings, right? By definition, science doesn't end, right? This is why you see headlines for cures of cancers. How many of those have we seen? Why isn't cancer cured if there's so many happy endings, right? And this is again because science doesn't operate that way. It's an incremental, right, addition of knowledge, right, where ultimately you never actually prove anything to be true, right? That's actually one of the philosophical constraints of how science works. If you think about it, science is really, you're just making sure everything is still okay until you actually prove something to be false, right? And because if it's still okay, that's your best fit answer, right? So, and the other thing with expert peer review, right, especially with the web, how many here have a blog? Anyone here have a blog? Anyone here have a website? No? Okay, yeah, right. This is just to say that there is the cult of the amateur, which simply means that to be the loudest voice in the room, you don't necessarily need to be the person that knows the most about the subject, right? And with the web, this is incredibly easy to do, right? Everything can be quite biased depending on what you read, right? So it's complete, media works completely differently from how science works, and that's a problem, right? It's not a problem if the public understands that, right, and realizes that, so that when they get their information, they've got that lens to kind of critique things. But by and large, I don't think that's the case, right? Does that make sense? So this is where I work. So I'm at the Michael Smith Labs. We are a multidisciplinary unit. There's about 15 faculty. My colleagues range in all sorts of different disciplines, from botany to zoology, microbiome, medical angles, statistics, engineering. We are a multidisciplinary unit. So my faculty position, I worry about science education and science literacy. So I thought I'd tell you a couple things that we do in the lab as well, just so you get a sense. Okay, we actually do a lot of different, because my mandate, I have two mandates in my lab. And the mandate is to train scientists in my area of expertise, which happens to be molecular genetics. So, if you want to learn molecular genetics, we host workshops and things like that where you can learn molecular genetics. But the second mandate is simply to talk science to the public, right? Just sort of more about the stuff I've just been talking about for the last 20 minutes or so. Okay. Now, when it comes to, so I'll focus on the public stuff. Like, I'll mention a couple things. Like, one of the things we do quite a lot of is sort of advocate for science generally. Okay, and this is because, I mean, I could be academic in my talk about scientific method, but it has real-world effects, right? When people don't pay attention, there are things going on in the world, such as climate change, right? Access to medicine. The way biodiversity is perceived by economies. There's all sorts of different things that actually have real-world consequences here, and maybe more importantly, to parts of the world that are a little less fortunate than us, right? Where actually understanding the science is actually quite important, right? This is actually a picture of a bunch of environmentalists hanging out at Copenhagen. In 2009, there was the big UN conference for climate change. And they're spelling out the word 350. Do you guys know what 350? Do you know anything special about the number 350? 350 parts per million is a calculated number of the amount of CO2 you want in the atmosphere, right? There's lots of assumptions. This assumes that CO2 is the primary driver within greenhouse gases, right? But this is the number that you want to maintain status quo, right? To sort of keep temperatures more or less the same as they have been, right? Do you know where we are right now? Does any?
392.
We are at 392. So we're already over, right? And actually this past year was the highest year for amount of fossil fuel CO2 emissions, right? It's always been going up except in 2009 when we had the economic downturn. It went down a little bit, but now it's full steam ahead, right? So here you have a situation where there is science that is telling us, right, that climate change is happening, and we have a pretty good idea of why it's happening. And not only that, we have a pretty good idea of what will happen, right? And yet, a lot of the policy that's formed around what government does is more or less ignoring it, right? So this is an example. And you know, as a lab that likes to talk about science, we do focus on, you know, trying to get the science out there. Like what? Like how do we know climate change is real and all of these things, right? I hope everybody knows what this is. Everyone knows what this is. If you don't, then I might make fun of you. This is sort of a mathematical representation of the first freaking law of thermodynamics. Okay, the first law of thermodynamics. Okay, everyone in this, if you don't know it, you should know this. Right? This is, you know, if you're a literature student, you know Shakespeare, right? That's a no-brainer. If you're a science student, you know the laws of thermodynamics. The first law simply states that energy cannot be created or destroyed. It is the conservation of energy. It's such an intuitive thing, but it is so fundamentally important in sciences because it provides a mechanism for bookkeeping, right? If you've got energy in the form of heat, right, dQ, or in the form of internal energy, right, such as, what's an easy example? Oh, if water can be a solid like ice, or if it can be a liquid or a gas in the form of internal energy, or in the form of work, where it's actually able to push things, do work, right? You've got to account for it. This isn't rainbows spouting rain. This isn't rainbows coming out of unicorns, right? This isn't glitter coming out of nowhere. Energy must be accounted for, right? And the first law of thermodynamics is one of the principal tools people can use in climate models so they know what happens to the heat that's trapped in here. And they can make predictions about things like storms and this like, right? What is air and water moving? Right? It's doing work, right? What is an ice cap melting, going from solid to a liquid, right? And changing sea levels and changing salinity of the oceans. It's changing its internal state, right? They add up. And yes, this is a simple equation, right? But when you factor in all the other physical laws out there that people have determined over the millennium, these models are actually, they're pretty good, right? And there's ways to validate them. So, you know, there's a disconnect, you know, because when we interact with the public, everyone seems to agree that the Earth is getting warmer, right? That there seems to be an agreement in that. It's funny, the reasons why people think that tend to range. Ranked very low is always because the scientific research says so, which is, oh geez, don't get me started. Usually the highest rated reason for why people think the temperatures are getting warmer is because they look out the window, like literally, oh, it seems warmer out there. Right? But people agree with that, right? And there's tons of very strong data that shows that CO2 levels are indeed increasing, right? And the fact that CO2 traps heat, this is very well defined. So you've got these facts in place, right? And in conjunction with something like the first law, you can do the math, you can do the modeling, right? You can do the science to show that the two, CO2 levels and temperature, there is a causative agent here. It's not just correlation, right? And with things like this, you can actually model what's going to happen. You can model the fact that more work will be done. Therefore, that could translate into extreme weather. You can model the fact that, you know, ice will melt at a certain degree, and that will translate to sea level. All of these physical changes that modeling tries to give you insight to, right? So we do a lot of advocacy work, right? And that's simply because, I mean, to be honest, I don't know, the public doesn't really get it. I mean, you know, we're having a difficult time with things like CO2 levels and our energy needs and sort of adapting to it, right? We can blame big oil and things like that, and I think they have a role in it. but at the same time, there's also an element where we are involved as consumers. This is actually a close-up of a picture by a digital artist named Chris Jordan. And what he does is that he makes photo montages of consumption, right? So this is from a piece that is essentially the number of plastic bottles used in North America every 5 minutes, okay? And we're zoomed in here, okay? And so I can zoom out, right? So you get a sense of how many plastic bottles that we use in North America every 5 minutes, okay? I'm actually still zoomed in, so let me zoom out again. So here's the final graphic, right? Based on 2006 stats, it's estimated that up to 2 million plastic bottles are used every 5 minutes in North America, right? We like our stuff. And you know, some of us might say, well, we can recycle it, right? And yes, I'm sure most of this gets recycled. We're kind of savvy with that regard, at least in, yeah, right? But that takes energy as well, right? It's not, right? Laws of thermodynamics, if you want to start moving things around, that's going to take energy, right? Okay. So we advocate. We do a lot of advocacy work as well. Another thing we do a lot of things for kids. Okay, and so that, you know, conventional examples are running field trips, but I'll show you a project we started about a year ago that's a little bit surreal. So this is a bird. I'm hoping everybody, since you're coming to a talk about biology, is aware of that. I'm kind of curious. Do you know what this bird is? Put your hands up if you can identify this bird. Okay, 2, 4, 5, 6. Okay, that's actually pretty good. So this is maybe about 50, 40 people here. So we're talking about 15% of the room knows what this bird is. This bird is a European starling. Okay, and the reason why I put this up is because this bird is everywhere. Like, it is everywhere. In fact, I could say quite confidently, I know for a fact that you have interacted and have seen this bird many times, okay? Especially in temperate regions, it's always up there in terms of most populous birds that are around. If you've ever gone to the coastline and you see sort of these huge swarms doing these really cool things where they're making these funky shapes as they're flying around, those are these European starlings, right? And they're everywhere, and yet, you know, we had maybe 15% of this room, right? And I usually, you know, when I show this slide to other lectures or other public talks, it's actually usually lower. It's about 3 to 5% know what this bird is in Vancouver, right? But you've interacted with it. Like, how does that make you feel? This is something that's like part of what you see, right? And it's there, and yet we don't really have this cognitive recognition of it. On the other hand, I could put a picture up like this. So how many of you know what this is? Right. Yeah. So yeah, and the stats are actually even better when you go to schools, like high schools and elementary schools, obviously. And actually, there have been studies done on this, right? There have been Pokemon versus wildlife studies. I have a colleague based in Cambridge. He did a study about 7 years ago. It was actually published in Science. And what he did was he found in the UK, in his area that he sort of did the questionnaires, an average 8-year-old, right, cognitively can recognize up to 120 different characters. 120 different characters. By the same token, when they did the exact same sort of experimental design for the most popular birds and plants and animals in the UK, that 8-year-old was maybe able to recognize about 30, right? So there's a big disconnect for something that is, well, not real, right? And things that are real. And it gets worse, right? Because it's not just identifications. Those kids could characterize those Pokemon creatures to no end, right? They knew what they were all about, hit point, all of these stats, right? And quite often with the animals and plants, they knew, oh, that's a robin, but really they couldn't really say much else, right?
looks like a hamster. That's why they know it.
Yeah, yeah. Well, there's lots of reasons for this disconnect, but one of the projects we started about a year and a bit ago was that we thought we would try a crowdsourcing initiative. So we actually put this information up into the web with some letterhead, right? Basically saying that kids know more about Pokemon than they do about the world around them. Okay. And then we just sort of sat back and waited to see what would happen, right? So I'm pleased to tell you that after about a year and a quarter, it's been incredible, right? So we have a community of artists who are donating art, right? And have figured out a submission systems. We have a community of curators, which are predominantly people with science background, who actually make sure that the information on the cards is scientifically sound. We have a community of gamers, feisty bunch. My role is primarily as a moderator, just to make sure everyone's nice. And when people aren't nice, it's usually there's a gamer involved. Just something I've noticed. That's anecdotal, but that's something I've noticed. We've had communities of educators, obviously, who might be interested in such a resource. Programmers, computer programmers, and this was a big one. We had a group of programmers actually come up with a WordPress template, so it's open source, so that you can, sort of essentially enter data, and it would aggregate the image, the curated data, and spit out a card that looks nice. And not only that, when you print this website, right, this page, it will give you a 3x2 picture in high res of the cards there, so you can actually cut them out nicely.
Can they battle each other?
Yeah, so there is a game. There is a game, and the game right now is more about ecosystems and how you can screw them up. So, but it's crowdsourced. I'm actually waiting for someone to design a game where you can pit Pokemon cards against these cards, right? But that hasn't happened yet, right? And but it's been quite wild, like the way this has sort of evolved in spurts, sometimes very slow, sometimes dramatically, different types of community. Early on, we had a community of IP lawyers, right? Because when we actually started out with the name, the children that we sort of asked, because we have quite a lot of kids coming through the lab, liked the name Philomon. Philomon. That was actually the name of the project. And it's still affectionately called the Philomon Project. But then we had some IP lawyers get on the community forums and just sort of advised us that Philomon, there's some indirect trademark infringement there, and that you may want to be careful of that. And so their reasoning was that Hasbro probably wouldn't have an issue with us using the Mon term, even though the trademark infringement just means that we get a slight plus out of it, right? Because just because they hear the Mon, they realize that it might be a game and there might be cards involved, right? But they probably wouldn't have an issue with us because we're open source and free and educational and all of these things. But they might have a problem with it setting a precedent, right? They'd be afraid. Actually, one lawyer said, yeah, they'd be worried about something like Pornomon being created if they let this one slide, right? So it's bizarre. There's all of these different expertises coming in to help, kind of go into this project. And lately, the newest community that's really taken notice is the museum community. So we're currently piloting with a couple museums the production of high-quality decks that you would need to pay for at the museum or online, where the museum can use it as a source of fundraising for projects, but at the same time, the community can now get like high-quality cards other than the ones they print. And not only that, maybe the cards are rare. Rarity is a big deal with some of these gamers, right? So here's another example of some of the kind of strange things we do, right? Here, this was in line with the International Year of Biodiversity. So again, even though it's with kids, in this case, there's an element of science advocacy, right? Which is what my lab is very interested in. So I just want to finish off, right? That I think above and beyond anything else, even if you don't go into communications or something of that matter, I think you being an advocate is very important, right? I said my dad beat up Bruce Lee, right? My dad's quite ill right now, and he's ill because he has something called SCA3, which is it's a genetic disorder, and it's one of these autosomal dominant disorders that you can test for. And I remember thinking, oh, that's so cool, right? Because here I am, a geneticist, a teacher, and I'm actually going through the textbook ethical nature of a genetic test because I had to get myself tested to see if I had this particular neurodegenerative disease, right? I tested negative, but at the time it was sort of like, you know, as we were going through it, I was thinking to myself, I can test myself. I have a molecular genetics lab, right? I could find out more information. So there was an element where I actually thought it was very cool. Now, as the years have gone by, and I can see my dad going through the disease, right? And he's at the point now where it's obviously not pleasant at all. You know, I don't think it's so cool anymore, right? And again, it sort of speaks to the power of perspective, right? And it's quite important as people who are scientists or learning about science, you do realize these other perspectives, right? You know, by turns, you know, this kind of episode has made me feel excited for science as I learn more about SCA3, right? It's made me feel inspired as I learned about people who are studying this sort of thing. It's made me feel frustrated because the science is a little slow, angry even because some of things like stem cell technology is one type of field that would have really helped in this particular disease. And there's a whole bunch of different cultural and political context that is affecting how something like stem cell research is happening, right? So this perspective is quite key. And even though you don't turn into a communicator or a PR or a teacher, I can bet that all of you here, one day, like a ton of bricks, it will hit you that what you're learning here, like how science works, is actually pretty damn important, right? And it's something that you would probably feel strongly enough that you would want everybody to be on board, right? And I think for that, I'll just leave it at that, and I'll take some questions. So thanks.